something yesterday when I told you, write out the formula when you're doing those, okay? If it's just straight probability, there is not a formula required. But if it's something or something, that's when we had our formula. Remember yesterday we had the probability of E or F equals what?
Probability of E plus probability of F.
Minus
probability of E and F.
And sometimes we didn't have to use that E and F piece when
When they did mutually exclusive.
if they were mutually exclusive, because that meant the probability of E and F would be 0. So in general, we had two versions of this rule. This rule, or this version, could be used all the time and just plug in a 0 if you know they're mutually exclusive. This is for an OR statement. So OR basically means to add. So if I said I want to know the probability that it rains or there's lightning tonight, you'd have a probability that there was rain plus the probability there's lightning minus the probability of both. If I ask for and, the probability it rains and we win the game tonight, okay, then that is talking about multiplication. Now our rule is going to depend on if the events are independent or dependent. So that's the first piece. Independent events. The occurrence of one does not affect the probability of the other. And dependent, the occurrence of one does affect the probability of the other. So I'll let you write and then I'll talk about it. Mutually exclusive means both events can't happen. You know, if you think about like a Venn diagram, mutually exclusive, what we were doing yesterday, basically meant there would be no overlap between those. Okay, if I were talking about we have a football game in Illinois tonight and a football game in Monroe tonight, could both of those things happen at the same time? In the same night?
Oh, yeah,
not at the same night. Now, in the same week, yeah, maybe. Maybe they scheduled a makeup game and we've got that. It would be possible. But to happen at the same time, no. Those would be mutually exclusive. So, mutually exclusive means they don't overlap. Independent and dependent is talking about if they influence one another. So that would be like saying, I wore flip-flops yesterday and the softball girls won their game. Did my wearing flip-flops cause them to win their game?
Yes.
Would them winning their game cause me to wear flip-flops? No. So neither one had an impact on the other. Those would be independent events. Okay, now if I said, I'm wearing flip-flops today and it's raining outside. Okay, does my wearing flip-flops cause it to rain outside? No. Will the fact that it's raining change the probability that I wear flip-flops?
Yeah.
Yeah, it might. So would those be independent events?
It would not change if Miss Dyer wore flip-flops though, because I've
That is
never
true.
seen her wear anything but flip-flops.
Yes, Miss Dyer is a different scenario. But for me, I'm less likely to wear flip-flops if they're, you know, if torrential downpours, maybe I don't want to. So you have to look at it from both ways. So those would be dependent events because there is some relationship. It doesn't mean one causes the other, but knowing one changes the probability of the other one. Now, let's look at this example. We are just going to decide if these events are independent or dependent. Suppose you draw a card from a standard 52 card deck of cards and then roll a die. So the events, draw a heart and roll an even number. So I pick a card out of the deck, I get a heart. Does that change the probability that I'm going to come over here and roll an even number? No. Rolling an even number, would that change the probability of drawing the card I want? No. So those are what are called independent events. They do not affect each other's probabilities. B. Suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year. So I have two completely separate people from anywhere in the United States. Would one of them surviving this year change the probability that the other one does? No. So those would be independent. Okay, C. Suppose two 40-year-old women live in the same apartment complex. And now I'm saying the events woman 1 survives the year and woman 2 survives the year. Would those be independent or dependent?
I mean, I guess it could be dependent because if one passed away, like it
Because
could.
of something, like say there was like, I don't know, like a leak of something.
Okay, so like a gas leak in the apartment, or a fire, or influenza, or something like that.
I was gonna say like that, or the one dying can cause the other one to die because like you have that like grief or whatever.
Right. So if they live in the same apartment complex, we can assume like they have some kind of interaction with one another. Now, does that mean if one dies, the other one is going to?
No, it just
Absolutely not. But if one dies, could that change the probability that the other one would? Yes. So those would be dependent events. Are we okay with that? Now, if events are independent, then to find the probability of two or more things happening, we can use multiplication. So, or means addition. That's what we were doing yesterday. Today we're doing and means multiplication. So this is the multiplication rule. This rule applies for independent events only. The probability of E and F both occurring is the probability of E times the probability of F. Now, again, this is only if they're independent. So one has no bearing on the other one. We won't talk about what happens if for the dependent case until Monday. I put on here, this might be extended for more than two events. If I want A, B, C, and D to all happen, you just multiply all four probabilities. So you could do as many as you needed as long as they were independent. The probability that a randomly selected female aged 60 years old will survive the year is 99.186%. What is the probability that two randomly selected 60-year-old females will survive the year?
Is like multiply 0.99186.
So I'm just basically saying the first survives. If I could write. And the second survives. So by our and formula, all we have to do is take the probability of the first times the probability of the second. Now they're independent because if I just pick two random people, we're going to assume that probability of one doesn't impact the probability of the other, so I would just do 0.99186 times 0.99186. And we get point. So part B, the probability that 4 survive the year, what would you have to do?
Just multiply four, like four amount.
I could do this 4 times. Would you care if I just wrote it to the 4th power? You have 4 of them, same thing. So that would give me 0.9678. I'm going to add another one on here. Okay. I want you guys to think. So, this could happen 2 different ways, couldn't it? If I'm talking about Skyly and Lacey in their old age, it should happen that Lacey survives and Skyly doesn't, or Skyly could survive and Lacey doesn't, right? Or means what? Addition. Okay, so if Lacey survives, what's the probability she would survive?
49,9186.
What would be the probability that Skyly doesn't then?
Wouldn't we just take 1
0.00?
minus?
Right, they would be complements, so you would have to do 1 minus 0.99186.
0.0084.
Or, so we're going to add, if Lacey doesn't survive, that would be 0.00814, and Skyly does survive, 0.99186. Point 0.0161. So there would be about a 1.6% chance that one survives and one doesn't, out of 2 randomly selected 60-year-old females. It's the complement of surviving, so I did 1 minus the probability that they survived.
If I'm not surviving, I'm done. Just,
Yeah, there's no in between.
Right.
You survive or you don't.
oh, we never know.
Okay. That was kind of a tricky one, just to see how we were doing with it. Okay, let me ask you this question. Still with this scenario. So, same thing, same probability. What's the probability that at least one will die during the course of the year? At least 1 out of 500 randomly selected. Okay, so that could mean 1 or 2 or 3 or 4, all the way up to 500 of them do not survive. How do I find this?
All the numbers.
It's a lot of numbers. I don't really want to calculate that much, do you?
I don't know.
Could
Our calculator could probably do it.
could we find the probability that they all survived?
And then just say like that.
So you just do like 0.99, that number, to the 500th power?
So the probability that they all survived, you would just have to take this number times itself 500 times. So we can just write that as an exponent.
Yeah, I'd rather.
Which is 0.016. I'm going to keep a few decimal places for now. Then, if at least one of them dies, that's the complement. Either they all survive or at least one dies, right? So I could just do 1 minus the probability that they all survive. They are complements. We get 0.9832. So there, out of 500 women, there'd be a 98.3% chance that somebody doesn't survive.
So that's just like, that's 1 not surviving instead of like 2. or
This is
something.
at least 1. So it could be 1, 2, 3, 4, all the way up to 500. It's basically everything except
What about if it
everybody
said
surviving.
just one died?
Then we would have to, we would do it similar to the last one, but we will talk more next week about how to do problems like that. Okay. Let's try, why don't you guys see if you can do this next problem. So, a manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So, in order to make a claim, they have to be using it, and it has to be defective. Okay, so we just have to do the probability that they use it, and means multiply times the probability it was defective. So the probability they use it is 0.3. The probability it was defective is 0.1. You get 0.03. So there's only a 3% chance somebody is actually going to take them up on that 1-year warranty, which is the same thing as that. Yeah. Well, you calculate the same 10% of this times 30%. So it's the same calculation. All right. The last slide I have up here is optional. This is all stuff that we have written down already. It's just kind of a summary of what we've learned so far. So, rules of probability. We know that every probability has to be between 0 and 1. The sum of the probabilities has to be 1. We know that if our events are mutually exclusive or disjoint, they don't overlap. So yesterday we did, if they're disjoint, probability of E or F, you just add them. If they're not disjoint, you also have to subtract the overlap, which is on our formula sheet as well. We also talked about yesterday the complement is just 1 minus the probability of your event. And then today we added in, if they're independent, the probability of both happening, you just multiply. Okay? So, what I want to do is give you guys, we have a lot of time left. We will grade yesterday's homework at, let's say, 110. So then that will give you a little time if you had any questions over that to ask those. And you can also start this next